In this video, I'm going to discuss a little bit of what's often called the wave-particle duality in quantum mechanics. And so, aside from maybe Schrodinger's cat, the wave-particle duality is probably one of the things that is most widely known about quantum mechanics, and one of the things that makes it so, weird and strange and bizarre and all that. But then the question is, why do we think that particles are waves and particles at the same time? And so this isn't just something sort of postulated, in the same way that like the wave function collapse is. This is something that's actually been sort of experimentally verified. And so I will go through three of sort of these seminal experiments that have sort of demonstrated this wave-particle duality. And so in the first one is the double slit experiment, which is sort of what showed that fundamental particles, including matter particles like electrons, are actually have a wave property to them. All right, so if we take a Gaussian wave packet, which is something that looks kind of like this is what is meant by a Gaussian wave packet right here. So it makes this sort of Gaussian curve, this normal distribution that looks like that around where the particle is sort of located. So where it has sort of the highest probability of showing up in the middle there. And so a Gaussian wave packet, which is a free particle, is a superposition of states parameterized by the wave number k, which is just related to the energy here. So you can kind of think about it as being sort of related to the energy there. And so this is the superposition. So it's actually a continuous superposition, which is why we are taking the integral rather than just a summation. And so that's an integral over all the different energies here, all the different wave numbers there, where this phi of k right here is just equal to this, where n is a normalization factor. And so to get the wave function at future time t, we added this factor here, which is just the sort of time dependence operator. You can think about it like that, where the e of k here is equal to this, which just comes right from this relationship right here. It's just the algebraic manipulation of that. And so we get this as our as our superposition right here. So when we evaluate that, we will get this as our wave function right here, which is a Gaussian curve. So we have this constant out front right here, but then this exponential term right here is what gives us our Gaussian function. So when we multiply this by its complex conjugate, or if it's easier for you to think about squaring it, which is the Born rule, then we get the probability of finding the particle, which will then give us this right here. And so that's the probability of finding the particle sort of over space, so over this space x here, where the width of the Gaussian is given in the exponent by this right here. So when we're talking about a Gaussian, so we can have a Gaussian that's very shallow like that, or we could have one that's very centralized like that. And so this is just giving us the spread of the Gaussian here. And so we see that this actually has a time term in here. And so what that means is that the uncertainty of the particle increases with time. So if we start with sort of a very narrow wave function right there, over time it will become a much more spread out wave function like that. And in fact, the rate of spreading of the Gaussian increases with time, because we see that it's squared there. So the momentum, however, is not a function of time, and so it remains the same over time. And so that's why the Heisenberg uncertainty principle is an inequality, since it can be arbitrarily large. So this is the version of the Heisenberg uncertainty principle we're kind of talking about here. I just wrote this one here because there is actually this other Heisenberg uncertainty principle that is with the change in time and change in energy. But we will be focusing on this one right here, which is the position and the momentum. So the sort of spread of the position in the momentum has to be greater than or equal to h bar over 2. And so this spreading out is related to diffraction. So we have a plane wave moving toward a barrier with a single slit. So that's what it looks like right here. So if the particle passes through the barrier, so it passes through the slit right here, then it becomes a Gaussian wave packet. So we're essentially taking a wave that's so spread out that instead of a Gaussian, we're sort of modeling it as just a flat probability here. But then when we put it through the slit, it sort of brings it down into a Gaussian that looks like that. So it sort of brings all this in so that it's much more localized in a particular place. But then when we see when it comes out the other side, it actually starts beginning to spread back out. So that's what I have showing right here. So we can calculate the intensity or the probability of the particle moving at a velocity v being in a given, so now we're looking in a two-dimensional area behind the barrier. And so now we have this x dependence, but also this y dependence because we are in 2 dimensions. And so this is the Gaussian for that, for the two-dimensional intensity. So sort of the intensity that we will see that will actually look sort of like this right here. So we can see kind of put sideways right here are Gaussian right there. And so if we sort of shine a beam through a slit right here, then it will sort of be turned into a Gaussian, but then spread back out, and then it can hit our detector looking like that. So now if we have a barrier with 2 slits, so at x equals positive a and x equals negative a, then we will get 2 Gaussians. So one centered at x equals negative a and one at x equals positive a. And so we will obtain the linear combination of Gaussians. So this is the first Gaussian, that's the second Gaussian. So this is the one at x equals negative a and the one at x equals positive a right there. So those 2 Gaussians, when they start spreading out, will overlap, and we get this diffraction pattern that looks like this. And so we end up on our detector getting a pattern that looks like that, rather than sort of what you would expect if this was a just particle, which is that you would get sort of a a line right there and a line right there. But instead we get this diffraction pattern like this. And so this actually works even for matter particles, which was demonstrated experimentally by Davison and Germer in 1928. And so in my lecture notes, which will be linked to down below, I will have a link to this paper if you want to look at it. And so these have a wavelength lambda that follows the de Broglie equation, where here h is our non-reduced Planck constant. So we have our lambda being equal to our Planck constant over mass times the velocity of the particle. So then the frequency nu here, so that's the Greek letter nu. So my velocities have the arrow over them, and the nu does not, because those 2 letters look very similar. So when it's velocity, it has the arrow over it. When it's the frequency, it does not have it. So if you have a difficult time distinguishing those, that's how you can sort of distinguish what I'm talking about here. So we have our nu being equal to our velocity over lambda here. And so we have the velocity, because we're saying that the lambda is equal to this, then 1 over lambda is sort of equal to the reciprocal of that. So we have our velocity times this. And so that is equal to mv squared over h bar, which is equal to E over h bar, where E is energy, which is equal to the mv squared. And so our angular frequency is equal to 2 pi nu, and the reduced Planck constant is h bar, which is h over 2 pi. So our energy equal to our h nu is equal to h over 2 pi times 2 pi nu, and so we get that the h bar omega here is our energy. And so this is often the form that you will see energy written in quantum mechanics, with the reduced Planck constant in the angular frequency. And so that's why I made that clear there. All right, so that is the double slit experiment. And so the sort of takeaway message is that when you have your particle go through two slits here, so you have two slits, it's like your particle is going through both of them at the same time and then interfering with itself. And so we get this interference, this diffraction pattern here. And so that's how we know, and what was demonstrated by Davison and Germer, that this is actually true for matter particles as well, that matter particles have a wavelength and that they can interfere with themselves. All right, so now we can look at the experiments, and I'll be looking at two of them that show that fundamental particles are also very particle-like. So the first one is the blackbody radiation here. So a blackbody is just something that doesn't reflect electromagnetic radiation. And so if we have, some object here that's a black body, then radiation sort of comes into it, but it doesn't reflect it back out. So it just absorbs it. But the black body cannot perpetually absorb electromagnetic radiation, growing arbitrarily hot while the room in it is arbitrarily cold. So you can't just put a black body in a room and just have it sit there absorbing all the heat in the room. So the black body therefore radiates energy. So it's not reflecting it, but it is radiating it. And so this is what the black body radiation spectra look like here. So we have our wavelength here, and then the spectral radiance, which is just sort of the intensity of the light. And so it's looking at the intensity at different wavelengths for these different temperatures here. But in classical theory, what we would have is actually this black line here, which just sort of blows up to infinity. But what we see is that as temperature goes down, the wavelength goes up. And so when the temperature is going down, so at 3000 Kelvin here, the peak is at a higher wavelength than when we are at 5000 Kelvin right here. And as temperature goes down, the intensity goes down. So we see that this intensity is a lot lower than this intensity right here, where the intensity I is just the power, which is the energy per unit time being radiated here. So meaning that the higher temperature has more intensity or power or energy per unit time, whatever version of this makes most sense to you. But why does the intensity not just go up infinitely as the wavelength approaches zero? And so this is known as the ultraviolet catastrophe, where before quantum mechanics, when you did the calculation for it, you would actually get this, and it would predict that the intensity would just sort of go to infinity as the wavelength keeps getting shorter and shorter here. But when you actually experimentally do this, that's obviously not what you get, because you don't light a candle and get blasted with a bunch of UV and X-rays and gamma rays and stuff like that. But it turns out that the system, that the energy in the system is a distribution centered on this, where this K sub B is the Boltzmann constant, which relates energy and temperature. And so what we actually get is a distribution that looks like this, where it is centered here on the kb and times t right here. This is because the energy comes in packets that cannot exceed the energy in the system. So the energy absorbed by an electron can only have discrete values. It has a very low probability of exceeding this average temperature here. So the photons in the system must be values determined by the possible energy levels of the electron in the system. And so we have this right here. So this is what we now know, or at least this is, the sort of approximation of it here, that we have energy coming in for absorption, and it absorbs, the electron jumps to this higher energy state. You can also have these lower jumps here, but the important thing to notice is that, if these are the atoms in your system, then this is the highest emission that you could get. You couldn't have a higher emission than that, so you couldn't get a higher energy than what your atom can emit here. And so the intensity is given by, and so B here is our spectral radiance, which, as I said, is related to intensity. But the thing to notice here is this exponential down here, which is giving us our sort of Gaussian function here, centered around this k sub b times t. So the energy of the photon is given by this h nu in the numerator up here in the exponential term, and the available energy is given by the Boltzmann constant times temperature, which is given in the denominator here. And so we end up with a Gaussian curve centered around what's in that denominator there. And so that's why we get spectra that look like this, rather than like this black line here going to infinity, because you can't get energies higher than that, because there aren't atoms in your system that can emit energies higher than that. All right, and so the next thing we wanted to look at is the photoelectric effect. And so this is just using light to sort of eject electrons from a metal. And so we see right here we have these light particles coming in, they interact with the atoms down here, and then these eject electrons off right here. And so the amount of energy of an ejected electron is the energy, which is equal to the Planck constant times nu minus nu sub naught, which we can see is proportional to this h nu here, which is the energy of our particle. This nu sub naught here is the minimum energy required, which is often called the work function. And that's because our energy has to be greater than 0. And so this nu has to be greater than this nu sub naught. So this has to be positive right here. And so we can actually see what that looks like right here, where we see this is the frequency of light being shined on zinc in this instance. So we see that we're getting no electrons being ejected off of it until we finally get to light of this frequency right here. And now we start seeing electrons ejected off of that, where this stopping voltage is just sort of looking at the number of electrons being ejected off of there. And so this suggests that light has momentum, even though it has no mass. So remember, momentum is mass times velocity here. But we can get the momentum of our light particle in this instance. So we start with the rest energy and the momentum. So we have E equals mc squared. We have momentum equaling mass times velocity. And so both of these have this mass term that we can use here and set them equal to each other. Then we just multiply both sides by the velocity, and we end up with this right here. But for light, our velocity is just equal to c, the speed of light, and so we end up with our momentum being equal to energy over c, because this c will cancel out with one of the c's here. But we also know from above that our energy is equal to this h times nu. And so we can then substitute for this energy, this h times nu right here. But we also know that c over nu is equal to lambda, which is our wavelength. And so we have that the momentum is equal to this h, the Planck constant, divided by the wavelength right here. And so that is our momentum for a light particle, which has no mass. And so what we see, we see above that matter has wave-like properties, which is what we saw with like the double slit experiment. And so it has a wavelength that is related to this. So our mass times our velocity. So it's inversely proportional to the mass times velocity. We also see that light has particle-like properties such as momentum, like this. And so this is known as the wave-particle duality, where whether you're like a matter particle, like an electron, or a light particle, like a photon, you have both momentum and wavelength. And so the momentum being sort of the matter or particle-like property of it, and the wavelength being the wave-like property for it. In practice, which by that I mean when we want to just shut up and calculate, what this usually amounts to is we just call it a particle when the description provides the best explanatory power. So when calling it a particle is just useful, then we call it a particle, and when calling it a wave is useful, then we call it a wave. But that's fine when you just want to shut up and calculate. But if we want to think about the ontology of such a thing being both a particle and a wave, this is a massive discrepancy, because a particle, sort of by definition, has a very definite position. It has a definite sort of momentum here. So our momentum here, it has a definite position here. But when it's a wave, when you have a wave-like property, your position is sort of spread out throughout this wave. And if you take the Fourier transform, you'll also see that the momentum is spread out, that you have multiple different momenta to it. And so this is, a very, like I said, a massive discrepancy here. So, ontologically speaking, this is kind of a problem for the ontology of what we are, of what we're interested in here. But anyway, I hope you found this video interesting, and I will see you in the next one.